For most of human history, Andromeda was a rumour of light, an ink blot on the night, a thumbprint on the glass dome of the sky. Sailors saw it, shepherds saw it, a smear you could miss if you blinked. Some said cloud, some said ghost, and a few, the bold few, whispered, what if it's another island of stars? The answer, when it finally arrived, broke the border of the universe we thought we lived in. Andromeda wasn't a puff of gas inside the Milky Way. It was a grand spiral, a metropolis of suns on a slow-motion collision course with us, a future our descendants will inherit. Tonight we'll peel back its layers, the long argument that changed astronomy, the ingredients hidden in its light, the rare stars and the sleeping black holes, the invisible matter that binds it together, and the audacious question, could something we create one day cross the gulf to meet it? This is a story of doubt, proof and wonder, a story of two galaxies that will dance, fuse and wake newborn suns in their wake. Settle in, dim the lights, let your eyes adjust to ancient photons. If you like space stories, please like and subscribe. Your support will help us make more videos. Nebula or galaxy? The great debate that changed the universe. Picture a time when the entire cosmos fit neatly, comfortably, inside the Milky Way. That was the early 1900s. Astronomers peered through smoky domes and brass eyepieces at faint world smudges sprinkled across the sky, labelling them spiral nebulae. Pretty? Absolutely. Mysterious? Completely. But were they clouds inside our galaxy, or entire star cities of their own? That single question split the field. On one side stood Harlow Shapley, the cartographer of our galactic neighbourhood. By mapping globular clusters, those glittering, spherical beehives of ancient stars, he argued the Milky Way was staggeringly large, far bigger than most had guessed, and that the sun lived out in the suburbs, not at the centre. If the Milky Way was that vast, he reasoned, there was no need to invent other galaxies. The spiral nebulae could simply be internal features, nearby clouds, star nurseries, or odd scraps of gas tucked somewhere within our colossal home. Facing him was Heber Curtis, champion of the island universes. He looked at those spirals and saw more than mist. He saw structure, arms, dust lanes, and, crucially, novae that flared and faded in ways suggesting great distance. If the explosions in Andromeda were the same kind we witnessed in our own galaxy, then their dimness implied Andromeda must be far away. Not hundreds of light years, not thousands, millions, far beyond the Milky Way's rim. The standoff erupted into a public showdown in 1920 at the Smithsonian, remembered as the Great Debate. Shapley brought scale and confidence. Curtis brought clues and contradictions. The evening didn't crown a victor. In truth, each man held a part of the puzzle. Shapley was right about the Milky Way's grandeur and our off-centre address. Curtis was right that those spirals were more than local weather patterns in space. The tie would be broken not by rhetoric, but by a clock, a cosmic clock, hidden inside a special kind of star. Earlier, Henrietta Swan Leavitt had discovered that certain pulsating stars, Cepheid variables, keep time with exquisite regularity. The longer their pulse, the brighter they truly are. That relationship, period to luminosity, was a ruler stretched across the void. If you could measure a Cepheid's rhythm and compare it to how bright it looked from Earth, you could compute its distance. No guesswork, no hand-waving, just math and light. Enter Edwin Hubble and the 100-inch Hooker telescope atop Mount Wilson, then the world's sharpest eye. In 1923 and 1924, Hubble sifted the grainy speckles in Andromeda and tagged a variable star with a tiny triumphant note on his photographic plate. VAR. A Cepheid, a cosmic metronome, ticking in another system. When he crunched the numbers, the verdict stunned the community. Andromeda lay millions of light years away. That put it safely, decisively, outside the Milky Way. Overnight, the universe ballooned. The Milky Way wasn't the universe. It was one galaxy among uncountable others. Each spiral in those plates wasn't a cloud. It was a city of stars, with neighbourhoods, histories, and destinies of its own. And that faint smudge that had teased stargazers for centuries, it resolved into a sprawling spiral bigger than our own, barreling toward us at cosmic speeds. Not a neighbourly wave, more like a slow-motion rendezvous set for billions of years from now. It's hard to overstate how radical that shift was. Humanity went from living in the universe's supposed centre to occupying one citizen's apartment in a galactic megacity, then discovered that city was merely one block in an endless metropolis of galaxies. The Great Debate didn't just settle a classification problem, it rewired our sense of scale, possibility and place. Of course, big answers spawn bigger questions. If galaxies are everywhere, how did they form? Why do some blaze with starbirth, while others drift into quietude? What dark scaffolding holds them together when their outskirts spin too fast to obey visible gravity alone? And what, exactly, lives inside Andromeda's luminous lanes? Young star clusters, gas oceans, ancient relics, even the telltale wreckage of past collisions. Those questions turned Andromeda from a solved mystery into an irresistible laboratory. From Cepheid heartbeats to radio whispers, from infrared maps of dust to the ghostly fingerprints of dark matter, M31 became the test case for everything we've learned about how galaxies live, grow, and collide. Hold on to that image. An old glass plate, a faint smudge, and a star whose light pulsed like a heartbeat. The clue that unlocked a universe of galaxies. The star that measured a galaxy. A crisp night in the 1920s. On Mount Wilson, the 100-inch Hooker telescope fixes its gaze on a faint whirl of light. Glass plates click into place. In a dark room below, an image blooms, grain by grain, until a tiny point inside Andromeda stands out, sometimes brighter, sometimes dimmer, always on a steady rhythm. Years earlier at Harvard, Henrietta Swan Leavitt had uncovered the key. Certain stars with regular pulses can reveal their distance. Edwin Hubble measured that pulsing star in Andromeda, did the sums, and the answer landed like a thunderclap. This nebula wasn't in the Milky Way at all. It was another galaxy, more than 2 million light years away. At that moment, the sky changed. Our home wasn't the whole universe, it was one island among many, and Andromeda, once a smudge, became our nearest great neighbour, vast, intricate, and unimaginably far. After the shock, doubts and new questions. Hubble's distance to Andromeda blew the doors open, but the room it revealed was messy. Big ideas rarely arrive neatly folded, and this one came with wrinkles that took years to smooth out. First wrinkle, brightness. If Andromeda was truly millions of light years away, then it and other fuzzy spirals had to be staggeringly luminous to shine at all from such distances. Some astronomers found that hard to swallow. It was like seeing a porch light from the far end of a continent and being told, "Yep, it's just a regular bulb." The math checked out, but the scale shocked human intuition. Second wrinkle, what powers all that starlight? Back then, the engine of the stars was still a mystery. Nuclear fusion wasn't yet the settled story. If galaxies were filled with billions of suns, people wanted a solid explanation for why they could burn for billions of years without running out of fuel. Until fusion became accepted, the sheer glow of distant galaxies felt almost suspicious, like a magic trick waiting to be debunked. Then there was motion. Hubble soon found that most galaxies are racing away from us, the expanding universe picture. Great. Except Andromeda, our showpiece example, is actually coming toward the Milky Way. Contradiction? Not really. It's the difference between traffic on the highway and two cars in the same lane. The overall flow goes one way, but a nearby pair can still pull together. Gravity between neighbours can beat the gentle push of cosmic expansion. Still, for newcomers to the idea, it felt like getting two rules at once. Another complication: not every spiral nebula people had catalogued was a galaxy. Some were things inside our own Milky Way: star-forming clouds, planetary nebulae, supernova remnants. Sorting the true island universes from local lookalikes took time, and better instruments. Astronomy had to do some cosmic filing, and the labels weren't always obvious on first glance. Maps of the sky also showed something odd. Galaxies bunch up. Instead of a uniform sprinkle, they cluster in groups and along great invisible threads. Was that an artifact of limited telescopes, or a real pattern written into space? As surveys improved, the clumping turned out to be real and important. Gravity, especially from a lot of unseen mass, was at work on huge scales. Today we call that unseen mass dark matter, but back then it was just a hint that something heavy was tugging on everything. There were even questions about the yardstick itself. Cepheid variable stars, those reliable clock stars used to measure distance, come in more than one flavour, and early on they weren't perfectly separated. That introduced errors. The result? Distances needed polishing. Astronomers went back, remeasured, recalibrated. The big picture didn't change. Andromeda was still far, the universe still vast, but the numbers sharpened as the community compared notes and built better tools. Through all of this, the culture of astronomy adapted. The cosmos grew from one city to an archipelago, to a continent of cities, and then to a cosmic web stretching farther than anyone had dared to imagine. Each doubt didn't erase the breakthrough, it refined it. The story turned from a single headline, Andromeda is another galaxy, into a deeper narrative. How galaxies shine, how they gather, how they move, and how their histories are written in the light we catch from them. Inside Andromeda, a living galaxy. Zoom in on that hazy spiral until it fills your view. The middle gleams like a lighthouse, dense, old, steady. Around it, two grand arms curl outward, sprinkled with young blue stars and rosy clouds where new suns are being born. That's Andromeda up close. Not a flat picture, but a busy city of stars, gas and dust, always under construction. Start at the core. The light there is warm and golden because many of its stars are elderly, small, long-lived, and packed together. Buried in that crowd sits a giant black hole. It's quiet most of the time, not flinging out dramatic jets, but its gravity rules the neighbourhood. Nearby stars race around it like cars looping a roundabout, their speed a simple clue that something heavy and dark sits at the centre. Slide out from the core, and the vibe changes. The spiral arms are where the action is. You'll see patches that shine bluish, short-lived, hot stars that formed recently. You'll also spot pinkish knots and arcs. Those are star nurseries, clouds of hydrogen lit up by newborn stars. Think of them as construction sites. Gas collects, squeezes down, and a cluster switches on. Some of those stars will live fast and end in fireworks, feeding the neighbourhood with fresh elements that the next generation of stars will use. Dust threads through all of this like smoke. It doesn't sound glamorous, but dust is essential. It shades and cools gas so it can collapse into stars, and it seeds the raw material that later becomes planets. In visible light, dust makes dark lanes, like smudges crossing the arms. In infrared light, which sees heat, the same dust glows, and you can suddenly trace the scaffolding of the galaxy, a hidden skeleton that tells you where stars will likely form next. If you zoom farther out, past the bright disk that most photos show, Andromeda keeps going. There's a wide, faint halo, sparse stars, ancient clusters, and something invisible, yet massive. We can't see this something, but we feel it. Outer stars orbit much faster than they should, if only the visible matter were there. The simplest explanation is a big, unseen halo of matter that doesn't glow. Dark matter. You don't have to know what it's made of to notice what it does. It's the reason Andromeda holds together the way it does. It's the silent frame behind the painting. That outer halo isn't empty of stories. It's streaked with ghostly streams, long, faint ribbons of stars. Those are footprints of past meals. Over billions of years, Andromeda has pulled in smaller galaxies and stirred their stars into its own outskirts. If you follow the streams, you can literally read the merger history, like rings in a tree trunk. Some of the small companions are still here, close enough to see even with backyard telescopes. Two of the most obvious, M32 and M110, hover near Andromeda's glow. They tug gently on their giant host, and that tug leaves marks, a slight warp in the disk here, a lopsided arm there. Andromeda isn't symmetrical because its life hasn't been calm. Look for the star cities that orbit in the halo, globular clusters. Andromeda has hundreds of them, tightly packed balls of old stars. They're fossils from the early days of galaxy building. Some are classic and compact, others are puffier, a bit odd, maybe captured from long-lost neighbours. Together they map the galaxy's outskirts like lanterns along a dark road. Inside the disk, motion runs the show. The arms aren't solid pinwheels, they're traffic patterns. As material orbits the centre, gentle waves of higher density pass through, compressing gas and nudging it into star-making. That's why you see young stars tracking the arms. Those waves are where clouds get the squeeze they need, but the pattern is messy. A past encounter, a nearby satellite, or a lump of dark matter can kink an arm, break it up, or spark star formation off the main lanes. Andromeda's arms look a little uneven because gravity is always nudging, prodding, and reshaping them. What about the black hole back at the core? Does it matter to life out in the arms? Not day to day. Most of the time it minds its own business, quietly holding court. But during busier eras, say when gas falls inward after a close pass with another galaxy, it can wake up. Then the centre brightens and energy pours out. If you were living in the inner regions during such a phase, you'd notice a harsher environment. Today though, Andromeda's centre is in a calm mood, and the drama is out in the arms where stars are forming. Here's a simple way to picture the whole thing. The core is the old town, all history and deep roots. The arms are the suburbs, new builds, young families, lots of growth. The halo is the countryside, scattered with ruins and relics from long ago mergers. And wrapping around everything is the invisible mass that keeps the city from flying apart. That mix, old and new, calm and chaotic, makes Andromeda feel alive. It's not a single snapshot, it's a story in motion. And because Andromeda is both big and close by in galactic terms, it's our best lab for learning how galaxies really work. We watch stars being born and dying. We trace how gas flows. We see the fingerprints of gravity in the bends, kinks and streams. And the more closely we look, the more we realise this galaxy isn't another Milky Way. It's its own character, with its own scars and rhythms. The colours of creation, Andromeda's chemical fingerprint. Imagine you could hold Andromeda's light in your hand and tilt it, like a CD catching a rainbow. Those colours aren't just pretty. Each tint, each narrow glow is a clue. Astronomers use a trick called spectroscopy to spread that light into fine stripes, the way a prism turns sunlight into bands. In those stripes are tiny gaps and bright spikes, the telltale marks of elements. Read them right and you get a recipe for the galaxy. Start with the obvious ingredients. Hydrogen is everywhere. The simplest atom, the main fuel for stars. When clouds of hydrogen are warmed by newborn stars, they give off a soft, rosy shine. You've probably seen that pink tone in photos of Andromeda's arms. Helium rides along too, forged in the first minutes of the universe. Those two are the base of the soup. The rest, what astronomers call metals, meaning everything heavier than helium, comes from stars themselves. Think of a star as a slow kitchen. Small and medium stars bake carbon and nitrogen and then exhale some of it when they puff up late in life. The really massive ones run hotter and faster, fusing their way to oxygen, silicon and iron, before ending in spectacular blasts that fling those new elements into space. Over time, that stardust mixes into the next generation of clouds, and the galaxy's recipe changes, richer, heavier, more complex. Andromeda shows that change clearly. Near the centre, where many rounds of star making have already come and gone, the light carries strong hints of heavier elements. Farther out in the disk, the mix is a bit leaner, fewer metals, more like an earlier era. It's a gentle gradient, inside to outside, telling the story of where the cooking has been hottest and longest. Dust is part of this story too, not the dust bunnies under your bed. Cosmic dust grains made of carbon and silicates, smaller than smoke. They shape where new stars form by shading and cooling the gas, and they seed the raw materials that can later become planets. In visible light, dust looks like dark lanes. In infrared, it glows warm, sketching the hidden skeleton of Andromeda's arms. Follow that glow, and you can guess when nurseries will switch on next. Every now and then, Andromeda's chemistry looks off. A patch of gas moving the wrong way. A star cluster whose mix of elements doesn't match the neighbourhood. Those are fingerprints of old mergers, smaller galaxies swallowed whole, bringing their own flavours into the pot. Out in the halo, you'll find long, faint rivers of stars, tidal streams that carry these imported recipes, proof that Andromeda didn't grow alone. We can even read time in these patterns. Old stars in the outskirts tend to be poor in heavy elements. They formed before the galaxy's pantry stocked up. Younger stars in the arms are richer. They were born after the kitchen had been busy for billions of years. Put enough of these clues together and you can sketch a timeline. Bursts of star formation here. Quiet spells there. A few rude interruptions when a satellite galaxy brushed past and stirred the pot. If you're wondering where planets fit in, the metals matter. Rocky worlds need the heavier stuff. Iron for cores, silicon and oxygen for rocks, carbon for chemistry. That doesn't mean every metal-rich star has planets you could walk on. But the odds get better as the recipe gets richer. In Andromeda's arms, where new stars are still forming from well-seasoned gas, there's a decent chance many suns are ringed by disks of dust and pebbles, planet factories in progress. The light itself gives away the action. When gas is heated by young stars, certain colours blaze brighter. A cherry red hydrogen line, a deep teal from oxygen. Measure the strength of those lines across the disk, and you map where stars just formed, where winds and shocks are stirring the gas, where supernovae have salted the neighbourhood with fresh elements. It's like flying over a city at night. The colour and intensity of the glow tell you which districts are booming. And then there's the quiet ruler at the centre, the supermassive black hole. Most days it doesn't change the chemistry out in the arms, but if a future close pass funnels gas inward, the core could flare, bathing nearby regions in high energy light that alters gas and dust. Galaxies breathe like that. Inhale during calm, exhale during storms. The chemistry keeps a record. Fast forward a few billion years, and Andromeda's recipe will mix with ours when the two big spirals finally unite. The result won't just be a new shape in the sky, it'll be a blended pantry. Elements forged in Andromeda's starbursts and quiet epochs will be folded into the combined galaxy, shaping the stars and planets that come after. Today's colours are early notes in a long symphony. So when you see Andromeda's pink knots, blue clusters, golden core and smoky lanes, you're not just looking at scenery. You're reading ingredients, steps and timing, the cookbook of a galaxy still writing its next course. Hidden luminaries, Andromeda's rarest stars. Picture Andromeda as a grand library. Most shelves hold familiar volumes, ordinary stars living ordinary lives. But tucked away is a row of strange handwritten journals, brief, intense, and unlike anything else. Those are the rare stars, short-lived oddities that burn differently, behave unpredictably, and leave clues you can't get from the everyday crowd. Find them, and you don't just spot curiosities. You uncover fingerprints of recent events, shockwaves from old collisions, and hints about how this galaxy keeps changing. Start with the divas, luminous blue variables. They are massive, hot, and gloriously unstable. Stars that don't just shine, they perform. For years they blaze at eye-watering brightness, then erupt, flinging off layers of gas like stage costumes tossed aside. Through a telescope they can jump, fade, then jump again, as if someone keeps fiddling with the dimmer switch. Catch one, and you're looking at a life lived in fast forward, a prelude to a supernova. Where they gather, star formation spiked not long ago. Close by are their stripped down cousins, the Wolf-Rayet stars. Imagine the engine of a star exposed, the outer hydrogen blown away, the hotter inner layers on display. Their stellar winds roar, so strong they sculpt bubbles in the surrounding gas. They blaze blue-white, live fast and die young. A patch rich in Wolf-Rayets is a diary entry that reads, "Massive stars formed here recently." In plain terms, when you see them, you're standing near the fresh footprints of a star-making surge. Then there are the runners, hypervelocity stars. Most stars keep to the quiet choreography of the galaxy. These don't. Some get kicked when a companion explodes. Others are slingshotted by Andromeda's central black hole. They streak through the galaxy like sparks from a grinder, some on paths that will carry them out forever. Track where they came from and where they're going, and you sketch the invisible landscape. Gravity's hills and valleys, places where the galaxy once threw a punch. Out in the calmer suburbs, the outer disk and halo, you meet the old souls. Carbon stars, they're cool, deep red, dust-rich elders that dredge carbon from within and breathe it into space. That soot is not mess, it's raw material for the future. Dust that clumps into pebbles, rocks, and eventually planets. A scatter of carbon stars marks regions quietly stocking the pantry. Many sit in faint streams, the long dissolving trails of smaller galaxies Andromeda swallowed. Follow the red glow and you can redraw the paths of ancient mergers. Andromeda also hides a few monsters. Magnetars. These are neutron stars with magnetic fields so intense they could scramble a credit card from half a moon's distance. Most of the time they lurk, compact and faint. Then, crack, a burst of high energy light, a brief tantrum that echoes across space. On the opposite end sit tiny, dense, white dwarfs. Alone, they fade like embers. In tight pairs, one can sip gas from a neighbour until, whoomp, a nova flares, then fades. Those recurring fireworks tell us how common close binaries are and sprinkle their neighbourhoods with fresh elements. Put the pieces together and these misfits become tools. Luminous blue variables and Wolf Rayets point to hotbeds of recent star birth. Hypervelocity stars trace deep gravitational wells and pass slingshots. Carbon stars map old streams and the quiet recycling that seeds future worlds. Magnetars and novae mark the harsh afterlife of massive stars and the simmering embers of the small. Most of all, rare stars don't live long. Finding them is like finding wet footprints, the event that made them happened recently, cosmically speaking. So when you picture that graceful spiral, don't imagine calm. Under the postcard view, there's weather, sudden, fierce, alive. These brief vivid journals on the secret shelf change how you read the whole library. They prove Andromeda isn't a static pinwheel, but a restless story still being written, line by glowing line. Stellar congregations, overlooked star clusters. Imagine wandering into a city at night. From far away it's aglow. Up close you start noticing neighbourhoods, tight-knit blocks, sprawling suburbs, old districts with cobbled streets. That's Andromeda. Not just a galaxy of lonely stars, but a patchwork of stellar neighbourhoods called clusters, each with its own mood and history. The elders of the city are the globular clusters, compact spherical swarms with hundreds of thousands of ancient stars jammed into a space a few dozen light years across. They orbit Andromeda like lanterns on a wide, invisible avenue, and there are a lot of them, more than we see around the Milky Way. Peer into one, and you're looking at a crowd that formed when the universe was young, stars with low, heavy element content and long, steady lives. Their ages help set the galaxy's timeline. Their orbits sketch the mass, hidden in Andromeda's vast halo. Not every cluster fits the textbook. Some are extended clusters, still bound by gravity, but looser, puffier, less centrally packed. They blur the line between a classic cluster and a tiny galaxy. You can think of them as sleepy suburbs, fewer streetlights, more space between homes. Their sizes and motions hint that some might be the leftover nuclei of small galaxies that Andromeda swallowed, sanded down by billions of years of tidal forces but not erased. Then there are the faint fuzzies. Yes, that's really what astronomers call them. They're old, like globulars, but more diffuse and harder to spot, especially in the outer reaches. Their very existence is a clue. In a galaxy that's had its share of run-ins, these delicate structures shouldn't survive unless they were born in gentler environments and later drifted in, or unless Andromeda's outskirts are calmer than they look. Counterbalancing the elders, you'll find pockets of young massive clusters, bright blue and crowded with stars only a few million years old. These are the fireworks crews, lighting up regions where gas clouds recently collapsed. Some sit right in the spiral arms where you'd expect them. Others show up in surprising places, as if a passing gravitational nudge, maybe from a satellite galaxy, squeezed gas and kick-started a burst of star-making far from the usual factories. Chemistry adds another layer to the map. Many clusters share Andromeda's general makeup, but a fraction don't. They carry unusual ratios of elements, more like what we find in dwarf galaxies. Those outliers are smoking guns for past mergers, travelling clubs that kept their original dialects even after moving into the big city. Follow their trail, and you can redraw the paths of long-digested companions, now stretched into stellar streams, arcing around the halo. Speaking of streams, some clusters don't just sit still. They line up along faint rivers of stars that wrap the galaxy. That's the debris of cannibalism, made visible. Remnants of smaller systems ripped apart and slowly stirred into Andromeda's outskirts. Place the clusters on a map and you get contours of old collisions, like tree rings after a storm season. Closer to the centre, the traffic gets wild. Dust, glare and crowding make cluster hunting tough, but improved imaging has teased out dense groups near the core. They may have been shepherded inward over time, where tides and the central black hole's gravity reshape them. A few could harbour intermediate mass black holes of their own. Hard to prove, but the odd star speeds inside some clusters keep that possibility alive. What do all these neighbourhoods tell us? First, Andromeda is not a still photograph. It's layered. Ancient foundations, renovated districts and fresh construction, built by steady star formation, interrupted by mergers, stitched back together by gravity. Second, clusters are excellent witnesses. Because they're long-lived and tightly bound, they preserve memories. Their ages log when building boomed. Their chemical mix records which factories supplied the bricks. Their orbits outline the hidden scaffolding of dark matter. So the next time you see that familiar spiral portrait, remember the neighbourhoods under the glow. Globulars marking the old bones, extended and faint fuzzies hinting at past arrivals, young massive clusters flashing where the next generations are being born. Read the city right, and Andromeda stops being a distant blur and becomes a living place, with history, weather and plans for tomorrow. Black holes unveiled, Andromeda's quiet giant. Picture the busiest roundabout in a city at midnight, almost empty, yet every street still bends toward it. That's Andromeda's centre. The lights dim, the noise drops, and in the middle sits a silent heavyweight, a supermassive black hole. Supermassive sounds explosive, but Andromeda's central black hole is more librarian than rockstar. It isn't spraying out blazing jets or swallowing gas in a public spectacle. Most nights, it's quiet, so quiet that if you looked only for fireworks, you might miss it. But the neighbourhood gives it away. Stars close to the core race along curved tracks as if obeying a hidden traffic cop. Only something incredibly compact and heavy can choreograph motion like that. Zoom in further, and the starlight starts to do something odd. The very centre doesn't look like a single dot. It looks slightly off-centre, like a double glow. That's a telltale sign of a tight, whirling arrangement of stars, an eccentric little disk, circling the black hole. Gravity has stacked the city centre into layers, and the innermost lanes move fastest, like cars on a track leaning hard into a turn. How big is the thing in the middle? Enormous. Think tens of millions of suns worth of mass squeezed into a space smaller than our solar system. For a sense of scale, the Milky Way's central black hole is a bruiser. Andromeda's is the older sibling who hits the gym twice as hard. Yet mass does not equal mayhem. A black hole only puts on a show when it has fuel, streams of gas to heat and light up before crossing the point of no return. Andromeda's pantry is lean right now. A trickle goes in, not a flood, so the core glows faintly in X-rays and radio, like embers instead of a bonfire. Quiet doesn't mean unimportant. That centre acts like an anchor. It steadies the flow of stars near the core, shapes the nuclear neighbourhood, and keeps cosmic time in its own way. Think of it as the keystone that lets the arch stand, even if you don't always notice it. Where did it come from? Galaxies grow by merging, and each merger can bring along another central black hole. Over billions of years, those migrants sink inward and pair up. Two become one. First a tight dance, then a final coalescence that ripples space itself with gravitational waves. Andromeda shows other hints of a rough past, warped structures, stellar streams, which suggests its central giant may be the blended product of earlier collisions. That makes the core not just a destination, but a diary. What about black holes beyond the middle? Some may lurk in dense star clusters scattered around Andromeda, smaller, quieter cousins hundreds or thousands of times the Sun's mass. They're tough to catch. You don't see them directly. You infer them from how nearby stars hustle or how gas moves. Every once in a while, a cluster's internal speeds look too high for the visible stars alone, hinting there's a dark heavyweight hiding in the crowd. Could Andromeda's central black hole wake up? Absolutely. A passing cloud, a disrupted star, or a slow inward drift of gas could fatten the accretion disk and light the core like a beacon. Galaxies cycle through phases. Today's wallflower can be tomorrow's headliner. And one day, far ahead, comes the main event. Andromeda and the Milky Way meet. Their central black holes won't rush. They'll close the distance step by step as the galaxies tangle and settle. Eventually, the two giants will find each other in the new, merged core and spiral together. That final fuse, two monsters becoming one, will ring the universe like a struck bell. Dark matter's whisper, the invisible backbone. Imagine walking through a perfectly still night with a strong wind at your back. You can't see it, but you feel it shaping every step. That's dark matter in Andromeda, an invisible push and pull that holds the whole galaxy together. Here's the simple mystery. In a galaxy made only of the stars and gas we can see, the outer stars should move slow, like cars easing around a wide, gentle curve. But in Andromeda, those far out stars are zipping along almost as fast as the stars near the centre. By normal gravity and visible mass, they should fly off into space. They don't. Something unseen is providing extra gravity, tightening the galaxy's grip. We call that something dark matter. Picture Andromeda not as a flat spiral alone, but as a shining disk embedded inside a huge, transparent sphere, a halo, much larger than the visible galaxy. The spiral you see in photos is the lantern. The dark halo is the unseen hand holding the lantern steady. It outweighs the visible parts by a lot. Without it, the graceful pinwheel would unravel. How do we see the invisible? We watch its effects. Star motions map the hidden mass. Gas clouds that should drift instead curve and cling. Even light itself tattles. As it passes a heavy mass, its path bends slightly, gravitational lensing, letting astronomers sketch the weight of things that don't shine. Every clue points to a deep reservoir of matter that neither glows nor reflects. Dark matter. What isn't it? It's not just dust. Dust warms and glows in infrared. It's not simply a swarm of dim stars. A galaxy full of faint suns would still leak detectable light. It's not a few stray black holes, you'd need too many. Whatever dark matter is, it's different. Something that hardly interacts with light at all. Andromeda's halo isn't perfectly smooth either. Think of it like a fog with patches, slightly denser clumps where old swallowed dwarf galaxies once lived. We see their ghostly star streams wrapped around Andromeda like torn ribbons. Those streams trace out where dark matter clumps tugged and twisted stellar paths, ripples on an invisible sea. This hidden mass doesn't just sculpt Andromeda, it choreographs the whole local group. The Milky Way and Andromeda are approaching each other, not because the universe forgot to expand here, but because their dark halos are hefty enough to bind them together. In a few billion years, when they finally meet, the stars and gas will twist and mix, but the halos will simply glide through and overlap, their gravity setting the rules for the new galaxy's final shape. Could we ever catch dark matter in the act? That's the dream. Particle detectors on Earth listen for the faintest tap of an unseen visitor. Telescopes map how galaxies rotate and how background light bends, building a case file thicker every year. Some theories imagine new kinds of particles. Others wonder if our equations for gravity need a tweak on huge scales. For now, Andromeda's behaviour is a steady, quiet vote for the dark matter picture. If this all feels abstract, return to the night wind idea. You don't have to see wind to watch trees bow, flags ripple, and waves travel across a lake. Likewise, you don't have to see dark matter to notice its fingerprints, flat rotation speeds, clumpy streams, bound satellites, resilient spiral structure. The evidence piles up, and the silhouette of the unseen grows sharper. There's also a human angle. The same galaxy that once forced us to admit the universe is bigger than the Milky Way now pushes us to admit the universe is stranger than bright stars alone. Andromeda didn't just widen the map. It dimmed the lights and asked us to trust our measurements. That's science at its best. Following the trail, even when your eyes say, "I don't see it." The company it keeps, Andromeda's little galaxies. Big galaxies rarely travel alone. Look closely around Andromeda, and you'll see a buzzing neighbourhood. Tiny companions, faint star streams, and the long fingerprints of past encounters. If Andromeda is a great city of stars, these dwarfs are its suburbs, some cosy, some crumbling, all shaped by the pull of their giant neighbour. Two companions stand out in backyard telescopes, M32 and M110. M32 looks like a compact ember, small but intense, tucked right against Andromeda's bright disk. M110 is puffier and more spread out, like a smudge just above the main galaxy. Both have had rough lives. Andromeda's gravity stripped away their outer layers long ago, leaving them leaner and closer to the core. Think of trees on a windy cliff, trunks still solid, branches long gone. Farther out, the faintest neighbours are easy to miss. These are dwarf galaxies, dim, star-poor, and dominated by dark matter. They carry ancient stars, old, red and quiet, along with the occasional pocket of gas, where new stars still flicker to life. Some hug Andromeda's outskirts, others loop on wide, slow orbits that take billions of years to complete. A few seem to move in a surprisingly thin, tilted sheet, like a flock of birds sharing the same flight path. Whether that pattern is a cosmic coincidence or a clue to how Andromeda grew is still an open question, but it's a good reminder that galaxies don't just sit there. They organise, tug, and drift together. The clearest evidence of Andromeda's appetite is written across the sky as star streams, faint river-like arcs made of stars pulled from unlucky dwarfs. The grandest of these, the giant stellar stream, is a long ribbon curling behind Andromeda, like a scarf on a windy day. Each stream is a time-lapse of a small galaxy being peeled apart. Follow one and you can reconstruct the original orbit. Follow several and you can outline Andromeda's invisible mass, because gravity decides where those rivers flow. All that nibbling and tugging changes Andromeda itself. The outer disk is slightly warped, like a vinyl record left in the sun, probably bent by the combined pull of passing dwarfs. Gas gets funneled inward, feeding bursts of new stars in certain lanes, while other regions go quiet. Even the central bar and spiral structure can be nudged by these repeated flybys. A giant doesn't have to collide head-on to be changed. 1,000 small shoves add up. How do we find and weigh such dim companions? We layer different kinds of light. In visible images, dwarfs are barely their smudges, but long exposures reveal the telltale scatter of ancient stars. Infrared helps us see through dust and pick out red giants. Radio maps trace hydrogen gas. If a dwarf has any left, you'll hear its whisper at that specific radio note. And with spectra, the fingerprints of starlight, we measure tiny shifts in colour to track motions. Put it all together and you get not just a head count, but a family tree. Who's bound, who's falling in, who got shredded and when. Some companions are oddballs. A few extended clusters look halfway between a star cluster and a dwarf galaxy, too spread out to be a normal cluster, too tidy to be a typical dwarf. Others hold stars with unusual chemical mixes, hinting they were born elsewhere and adopted later. These misfits are precious because they preserve stories Andromeda has already tried to erase. Why should we care about these little guys? Because they are the fuel and the fingerprints of galactic growth. Dwarfs bring fresh stars and gas. Streams sketch out Andromeda's dark halo. Warped edges and ring-like patterns tell us what's been happening just beyond the bright disk. And when Andromeda finally meets the Milky Way, this whole entourage comes along. Some dwarfs will merge into the new combined halo. Others will be slingshotted onto wild orbits. The future Milkomeda won't just be two spirals blended, it will be a full local group remix. So the next time you see a wide field photo of Andromeda, don't stop at the shining spiral. Scan the margins. Those tiny smudges and faint arcs are not background noise. They're the chorus. They tell you where the galaxy came from, what it's doing now, and how it will face the biggest change yet.